guys, Mr. Gucci here with your 4.1 help video, this one for the frequency and energy video. Now, I'm not going to get too deep in the explanation of these problems. I'm just going to go ahead and solve them. If you're looking for me to explain what these different values mean, then please go and watch the video for this portion of the unit. Now, once again, with all these homeworks, first step is to put your name in. I'm Dave G. And put in your ID. I'm using my fake ID, 123456, okay? You need to put in your ID so that it will generate random numbers for you to use for the remainder of your homework. Now, these are going to be really straightforward problems. The only difficulty is going to be using the E function in your calculator, doing scientific notation correctly. So let's get to it. Okay, so the first problem here, a particular color of light has a frequency of 4.56 times 10 to the 14th hertz. What energy is contained in a single photon of that light? Well, we have a formula right here that says the energy contained in a photon of light is just its frequency times this value called Planck's constant. Planck's constant is just a value that tells us how much energy is contained per frequency in a wavelength of light or other electromagnetic radiation. Okay, it's a constant, it does not change, and so the formula is going to be actually quite simple. All right, 1 second, 4.56. So here we go. Problem number 1. All right, the energy contained in a photon of electromagnetic radiation, all right, is equal to its frequency times this Planck's constant right here. Okay, now the frequency given was, again, 4.56 times 10 to the 14th hertz. That's how many waves are coming at you per second, all right? And we're going to multiply this by Planck's constant, which is 6.63 times 10 to the negative 34th joules per hertz. This is a really small number, guys. This is like 0.3300663. Because again, it's a small amount of energy because it's how much energy is contained in just a single little poof burst of radiation released by a moving electron. Okay, so we're just going to put this into the calculator. All right, I'm going to plug it into the calculator. In fact, I'll plug this into Google's calculator. Here we go. I'm just going to go to the search bar here, and I'm going to go 4.56 times 10 to the 14th times Planck's constant, 6.63 times 10 to the negative 34th. And we get 3.02 times 10 to the negative 19th joules. All right, so 3.02 times 10 to the negative 19th joules. And that's correct. All right, that's correct. Let me go put that in here. All right, 3.02 times 10 to the negative 19th joules. This is not a lot of energy at all. But then again, it's just the energy that's being released by a single electron, all right, as it's moving around the atom. And those things are super tiny. They don't have a lot of energy. Okay, so that's problem number 1. Let's get to problem number 2. What is problem number 2? Problem number 2 says that a particular color of light has a frequency of 6.91 times 10 to the 14th hertz. What energy is contained in a single photon of that light? Well, folks, it's the exact same formula. So here we go again. Energy contained in a photon of light equals the frequency times this constant right here. Okay? So in this case, the frequency was 6.91. 6.91 times 10 to the 14th hertz. That's how many waves are hitting per second, about 691 trillion waves per second, times Planck's constant, which is 6.63 times 10 to the negative 34th joules per hertz. And once again, I'm just going to go and I'm just going to plug this in to Google. Okay, so here we go. 6.91 times 10 to the 14th hertz times 6.63 times 10 to the negative 19th joules per hertz. Let's take a look at what we get. 1 second. Okay, I messed up. It's 6.63 times 10 to the negative 34th. Hey, mistakes happen, guys. Mistakes happen. So let me try this again. Okay, 4.58 times 10 to the negative 19th joules. 4.58 times 10 to the negative 19th joules. That's correct. 4.58 times 10 to the negative 19th joules. All right. The energy here, 4.58 times 10 to the negative 19th joules. Again, a small amount of energy, but this is just the energy that's being released by a single electron that's moving up or down from an excited to a ground state around the nucleus of an atom. Let's try the last one of these first three, okay? I'm just going to get this equation down because it's the same one. Energy of a moving electron that releases a photon of light, it's equal to the frequency of that photon times Planck's constant, okay? So let's take a look back here. Problem number 3. Particular color of light has a frequency of 6.71 times 10 to the 14th hertz. What is the energy contained in a single photon? All right, so once again, the energy equals the frequency, which was 6.17. 6.17 times 10 to the 14th hertz times Planck's constant, which is 6.63 times 10 to the negative 34th joules per hertz. All right, so once again, I'm just going to enter this into Google. All right, here I go. 6.17 times 10 to the 14th. That's the frequency times the wavelength, or times the Planck's constant. 6.63 times 10 to the negative 34th joules per hertz. And I get 4.09 times 10 to the negative 19th joules. 4.09 times 10 to the negative 19th joules. That's correct. Now, guys, the reason why we keep getting the same approximate energy around here, it's all in the 10 to the negative 19th range, is because we're only dealing with visible light waves, which is a very small part of the electromagnetic spectrum. If we were to do, say, gamma radiation, which had a much, much, much higher frequency, you would see the energy also go up here. Whereas if we had like radio waves, which had a much, much, much lower frequency, maybe only a few thousand or million waves per second, then the energy would be much, much lower as well. And it's that low energy that makes things like radio waves totally safe. Those waves don't have enough energy to damage our molecules and atoms, whereas gamma radiation or ultraviolet radiation does have enough energy to damage the cells in our body, particularly our DNA. Okay, guys, this was problems 1 through 3. I'm going to make a video for numbers 4 and 5.